Uh, Basically, this next chapter is sequences and series, but we're going to start this answering the question, what comes next? And you've had these problems before. They show up on SAT, ACT, and we're going to talk about certain techniques. Now, some of them you don't need techniques. Like for this one, if I ask what comes next, you can look and say, well, okay, I'm going up by 2, so the next number is 11. Pretty easy, right? Next one, you ask yourself what's happening. I'm subtracting 7 each time, so my next number is going to be a 22. I guess I should put up here. So sort of the pattern for the example 1 is we're adding 2. The pattern for example 2, we're subtracting 7. So whenever you're adding or subtracting, those tend to be easier to figure out. The next one, I'm looking, okay, decimal. I don't like dealing with decimals that much. So if it's harder to figure out what's happening from here to here, then you think, well, instead of just starting at the first term, why don't I start at the second? And what's happening from here to here? Well, it looks like I'm multiplying by 5. What's happening from here? I'm multiplying by 5. So it looks like my rule is I'm multiplying by 5. So my next term in this case is going to be 125. And if you look at the next one, okay, from here to here, it looks like I'm dividing by 2. I'm dividing by 2, dividing by 2. So this is going to be, if you divide by 2, in general, your life's going to be easier if you keep things in fractions. So I'll make that 9 over 2. And also, even though you may think this means divided by 2 for future reference, your life will be easier if you think about it as you're multiplying by 1/2. So, what comes next? Now, we can ask harder questions, and I will in just a minute. But these are kind of the basic and a sequence is a list of numbers with a pattern. And how do you determine the pattern? The two most common patterns are you're either adding or subtracting a certain number, or you're multiplying or dividing. Kind of the trick is if you are adding or subtracting, that's got a special name. Those are called arithmetic. And anytime you're multiplying or dividing, these are called geometric. And just kind of a preview, today's just an introduction into sequences. Then, tomorrow we're going to talk about arithmetic. And then after that, we're going to talk about geometric and a host of other things afterwards. But our main goal here is, what comes next? How do you figure stuff out? So adding and subtracting is kind of easy, right? And sometimes they can get sneaky. And multiplying gets a little harder. And we're going to get to those. But I'm a little more interested in, well, what happens if it's not easy? Like, what are some tricks? Like, what if I gave you the sequence 3, 6, 11, 8, that's an 18, and 27, and 38. Now, so what do you do when it's not obvious what's going on? So what are some tricks? And the first trick I'm going to talk about today is something called differencing. And like in my first two examples, they're kind of, it was obvious what was going on. What's going on here, not so obvious. But there's this technique, differencing, and what differencing does is you say, well, if you don't see a pattern originally, you say, well, what's the difference from here to here? That's a 3. What's the difference from here to here? That's 5. What's the difference from here to here? That's a 7. What's the difference from here to here? That's a 9. What's the difference from here to here? That's an 11. Well, if you can't see a pattern in the original, what if you look at the differencing? What if you look at the differences? If you look at the differences, it's like, oh, I'm seeing a pattern. And if you see a pattern, then you can think, well, so if the difference here was 11, that means the difference from here to here is going to be 13. So if I add 13, I get 51. So that's a trick to figure out what's next. Is you're still looking for a pattern. If you can't see a pattern in the original, well, you look at the differences and see if you can see a pattern. all right? Okay. Of course, that's the easy one. What about the harder one? What if I give you -2, 5, 24, 61, and 121, 122. I need to copy the problem then, right? All right, give you a little time to write that one down. And again, the question is, what's next? You think, that looks really weird, right? There's a lot of stuff going on here. So you say, well, whenever you see just a list of numbers, you think, well, I don't know what's going on. Let's try differencing. So when I do difference the first one, okay, from here to here is a 7. What's the difference from here to here? What's that, a 19? Difference from there to there. 37. Difference from here to here. 91. Oh, 61. Well, that doesn't seem to help. Well, here's the interesting thing about differencing. Sometimes, if differencing the first row of differences, if you don't see a pattern, try differencing again. And so, let's see, that's going to give me a 12. That's going to give me an 18. That's going to give me a 24. And at this point, you're thinking, I don't know if you can see, but there's something in common here. Notice how we're going up by 6, going up by 6, going up by 6. So sometimes you can do, it's called repeated differencing. If sometimes when the numbers are really ugly, you do differencing multiple times, and at some point you might get a pattern, right? Of course, we have a pretty easy pattern here, and so now we know that from here to the next term, if this is a difference of 6, then this is going to give me 30, which means from here to here is going to be, if this is a difference of 30, that's going to give me 91. And if this has got a difference of 91 to here, this is going to give me 213. So I don't know how many of you have seen this, have done differencing before, but one of the tricks with differencing is, it's great if you get a pattern after the first one. And I'm going to put this down just for one more. Notice we got a count. Everything got to be, in that previous example, we finally got everything that was a 2. So notice we got a nice constant after 2 rows. This one we had a nice constant, but it took 3 rows to get there. The significance of the 2 rows and the 3 rows is going to be, I'll talk about that significance a little bit later. But when you're trying to figure out what comes next, differencing is a wonderful, is a good skill to have. All right, so what do you need to know about sequences today? Well, there are a couple of things about sequences. Right? First, how are you given a sequence? One way you're given a sequence is they will define them an explicit formula. And here's what an explicit formula looks like. Actually, let me back up just a little bit. In dealing with sequences, there's some terminology I want to make sure we're good, that everybody's clear with. So I'm going to bring back our first sequence that I had. So I had 1, 3, 5, 7, 9. And to talk about this particular sequence, we have positions. And anytime I deal with sequences, I put dashes. Textbooks don't tell you this. This is just what I do. I put dashes because when I put dashes, I know this dash is talking about this position. And when I put the dashes in, I'll say, this is my first position, this is my second, my third, my fourth, my fifth. Now, the way textbooks reference a sequence is they'll say A sub n. And a sub n, they'll give a formula, but when they talk about the first position, they'll say this is a sub 1, this is a sub 2, this is a sub 3, a sub 4, and a sub 5, where, this is the first position, the second, the third, the fourth, the fifth. But just in general, anytime you're dealing with sequences, particularly when the problems get tricky, it's in your best interest to put a bunch of dashes down and say, just so you know, have an idea what you're looking for. All right, now back to this. What the heck is an explicit? How do you define a sequence? One is I could just give you the list of numbers, but most of the time the way they defined it is there's this thing. It's called an explicit formula. In explicit formula, they tell you, they say a sub n equals, and they might give you something crazy like x squared plus, messed up that. Let's try that again. They'll say a sub n is equal to n squared plus 2. So let's, like some of your homework problems are going to be, they give you an explicit formula and they'll say, like, write down the first 3 or 4 terms. And if I give you an explicit formula and I say I want the first 5 terms, well, we're going to put 5 dashes. 1, 2, 3, 4, 5. And how do we figure out our 5 terms? Well, if I want to figure out the first term, a sub 1, plug a 1 in. Well, when I plug a 1 in, 1 squared is 1, 1 plus 2 is 3. Then I want my second term. And then I plug a 2 in, 2 squared, 4 plus 2 is 6. Do a sub 3, let's say 3 squared, 9 plus 2 is 11. I put a sub 4, well, 4 squared, 16, plus 2 is 18. And then a sub 5, 25 plus 2 is 27, so I end up with 27. I think I only wanted the first 5 terms. 1, 2, 3. Oh, whoops, I forgot there was an 18. And then we get 27. And so we have our nice little sequence. Now, if you think about these numbers, if you say 3, 6, 11, 18, 27, you're thinking those might look familiar. Well, there's a reason they look familiar. Remember this thing where we had to figure out the next term? The reason I wrote this formula, this explicit formula, notice that formula has an n squared. And when we were finding out the next term, it took 2 rows to figure out what was going on. Well, that's not a coincidence. If it takes 2 rows to figure out your answer, that means your formula is going to have an n squared. Now, I'm saying that because now I want to look at a more complicated version. And so I want to say a sub n equals n cubed minus 3. So given this explicit formula, I want the first 5 terms. So I'm going to have 1, 2, 3, 4, 5. Let's figure out what these 5 terms are. So if I want a sub 1, plug a 1 in. So 1 cubes 1 minus 3 gives me a negative 2. A sub 2, 2 cubes 8 minus 3 gives me a 5. A sub 3, what's that? 27 minus 3 gives me 24. A sub 4, 4 cubes 63. 64 minus 1, it gives me a 61. And then a sub 5, 125 minus that gives me 122. So if I plug these values in where position 1 is a negative 2, position 2 is a 3, position 3 is a 24, 64 and 122, where this explicit formula gives me this sequence. And if you're thinking those numbers look familiar, well, there's a reason those numbers look familiar. That was this next example. And I don't know if you remember, but in this next example, notice it took 3, we had to do differencing 3 times to get to a constant. Well, notice our formula had an n cubed. So if however many rows of differencing it takes to get a constant, means that your formula is going to have, that's going to be kind of the degree of your explicit formula. Now, as far as explicit formulas go, they're very useful as far as answering questions. Like, even if I give you an incredibly ugly explicit formula, like, let's say I gave you, let's move that down. This is a typical ugly formula. Here's my ugly explicit formula. And again, I want the first 5 terms, so 1, 2, 3, 4, 5. I want to find the first term. I'll plug a 1 in. Well, -2 to the first power is -2. 1 minus 3 gives me a -2. So my first position is a 1. I put a sub 2 in. -2 squared gives me a +4. And then 1 minus 6 is -5. So I get -4/5. A sub 3. Plug 1 in. Plug the 3 in. So -2 to the third is -8. 1 minus 3, that's also -8. So I get a 1. Plug 4 in, -2 to the fourth gives you a +16. 1 minus 12 is -11. So I get -16/11. And the fifth term, plug 5 in, -2 to the fifth is -32. And let's see, 1 minus 15 is -14. So end up with 16/7. The reason I actually wanted to do this particular sequence, sometimes when you're given a formula and you have a negative number raised to a power, actually not sometimes, all the time when you have a negative number raised to a power, I wanted you to recognize that your terms change signs, like every other term. It was positive, negative, positive, negative, positive. And what controls all of that is this negative number raised to a power. If it's to an even power, this ends up killing the negative. If it's an odd, the negative lives. And so that idea of the negatives living and dying is reflected in this sequence of numbers. Now, typically you like an explicit formula. The reason you like an explicit formula, if I say, give me the first 5 terms, you have no problem. I just plug in 1 through 5. Let's say if I give you a very basic one, let's say I gave you 2n plus 3. And I said, I want to know what the 10th term is. Well, that's real easy to figure out. You just plug a 10 in for n, so 2 times 10 plus 3. The 10th term is 23. And that's pretty much it. That's what an explicit formula. You got your nice explicit formula. If I want the first 5 term, you plug in 1 through 5. If I want the 10th term, you plug in 10. If I wanted the 100th term, you plug in 100. It's not a problem. I'm going to contrast that with what's called the recursive formula. Now, here's what a recursive formula looks like. Recursive formula has 2 parts. They have to tell you the first one. So they got to tell you the first term. I'll say the first term's a 2. And then they say something, and then they have something that may look kind of weird. I'll say a sub n equals so the a sub n we've already talked about. And this is that n minus 1 is a subscript plus 3. And, what if I want the first 5 terms? Again, I want the first 5 terms. How do you deal with this? Well, here's how you deal with it. First, I want my 5 terms. So 1, 2, 3, 4, 5. And just in general, the first term's easy. They tell us the first term's a 2. And students have had trouble with this in the past, so if you're struggling with it, that's okay. But I do want you to sort of understand this picture. As far as understanding the picture, what I want you to realize is each of these positions, I could call it 1, 2, 3, 4, 5. Right? That's what I could do. But what if I called this position n, then the next position is n plus 1, and this position is n minus 1. I mean, I guess I can call this n plus 2, and I call this n plus 3. But in general, you know, if I have this referencing where if this is position n, this is position n plus 1, n minus 1, or this is in position n plus 1. And here's how you interpret this. Each of these, it's saying the value of position n is equal to the value of the previous position plus 3. So this is saying the way I find this term, because depending on where the way I find this term is take this term and add 3 to it. So if I do 2 plus 3, that's going to give me 5. Now if I want to find this position, a sub n, if I want to find this position, then that's equal to this position plus 3. So that gives me an 8. If I want to know the value of this position, that's equal to the previous position plus 3, which gives me 11. And if I want to know this position, I guess I should put a sub n. This is a sub n minus 1, these are a sub n. So if I want to know the value of this position, it's equal to the previous position plus 3, which gives me 14. And you know, this is finding the first 5 terms of a recursive formula is actually, it's a little bit easier with the recursive formula than, I think it's easier than with the explicit formula. They're about the same. They're both not hard. If I just want to find individual files, it's just, you just one at a time. You just find, they tell you the first one, and then everything is kind of based on this first one. Like to find this one, you take this one plus 3, find this one, it's this one plus 3, find this one is 3. Here's the problem. The issue with recursive formulas is if I want to know the 10th position, there's no easy way to find the 10th position. You literally have to draw 10 dashes and compute all the way up to the 10th one, as opposed to an explicit formula where you just plug the value in. But let's look at another one. Let's say, another example, let's say I give you a sub 1 is equal to 3, and this time I tell you a sub n is equal to a sub n minus 1 times 2. So for this one, I'm going to put my dashes down. I want the first 5 terms, 2, 3, 4, 5. The first term's easy, they tell me. They tell me my first term is a 3. But now they're telling me that if I want to find a sub n, if I want to find this position, that's equal to this position times 2. So if I take this position times 2, that gives me a 6. Now I move this over. If I want to find this one, it's this position times 2, which gives me a 12. If I want this one to find, it's this position times 2, which gives me a 24. And over here, if I want to find this position, it's, the value here is this times 2, which gives you 48. So recursive formulas tend to be a bit of a pain. And let's see. Let me hit pause for a second while I'm. So the last little bit we need to do is, let's say I give you a list of numbers. So I give you -6, -3, -2, -3/2, and negative 6 over 5. And what I want an explicit formula. All right? So when I look at this, I've got to think, what do I do to get from here to here, right?